geometric Langlands theory. That's what.
Okay, so first I'd like to thank the organizer for inviting me to this conference. So this talk will have a lot of overlaps with Sam's talk last week, but I will try to introduce this theory or this problem from some different motivations, and I will try to provide some other perspectives to this proof. So also, still this talk is will focus on the basics. So if you are an expert in this area, or if you have heard similar talks from other people or from myself, you will get few new things from this talk. So, but let's start. So, okay, so Sam started the motivation from class field theory and from some other thing. I will start the motivation from Langlands conjecture. So here, our F will be a global field of characteristic P. So it's a function field, and this AF is ring of ideals. So roughly speaking, Langlands conjecture, global Langlands conjecture says you should have a correspondence between Galois representations and automorphic representations. If you restrict to irreducible ones and irreducible cuspidal ones, you will get a bijection, which is a theorem by Greenfield in the case n equals to 2 and by Fogg in the general case. So this was a theorem like before 2000, so published after 2000. It's around that time. So, but this bijection is not an arbitrary one. So you need to have some requirements to make it, in some sense, a unique bijection. So one of the requirements I want to mention is that this bijection should match some natural invariants defined on both sides. On Galois side, you should use some Frobenius eigenvalues, and on the automorphic side, use Higgs eigenvalues. So the meaning of these eigenvalues will be explained now. So we start from the Galois side and introduce the Frobenius eigenvalues for Galois representations. So there are some notations, but the idea is if you consider a local place, in other words, a prime ideal of the ring of integers OF, you consider X, and you consider a lift of X inside the ring of integers in the algebraic closed field F bar. So then you can consider several Galois groups. So you can consider the Galois group for the residue field, which is equivalent to Z hat. You can also consider the decomposition group, subgroup of this epsilon Galois group of F. So this is the group that fixes this X bar. You can also consider the kernel of this map, which is the inertial group. So suppose our Galois representation is unramified at X, which means this inertial group acts trivially on your representation. Then you can define some numerical invariants called Frobenius eigenvalues as follows. You start from the Frobenius element. So more precisely, the geometric Frobenius element inside this Galois group of the residue field. You lift it to an element in the decomposition group, and you consider its image under this representation map, this sigma. So because this Ix bar acts trivially on this representation, so this image does not depend on this lift. Also, if you change this X bar, so you will get some conjugacy, other subgroup of this Galois group conjugate to this decomposition group. So therefore, the conjugacy class of this element is well defined. So in other words, so we obtain a well-defined conjugacy class inside GON. So then you can consider the invariants attached to this class. Namely, you can consider all the eigenvalues. So these are called Frobenius eigenvalues. So there are n of them, and it doesn't matter which order you put these values. So any questions so far? Okay, so let's look at the automorphic side. The automorphic side, these numerical invariants are called Higgs eigenvalues. So they are the generalization of classical Higgs operators on modular forms. So I will define it in the following way. So you can consider this double quotient. So this is this F is the local combination of F at fx is the local combination of f at the place x, and this Ox is the ring of integers inside it. You consider this double quotient. And consider complex supported functions on this double quotient. This is known as spherical Hicks algebra. The algebra structure is given by convolution. So as we will later see, this is actually a commutative algebra. So we denote it by Hx. And now suppose your automorphic representation is unramified at x. Then your representation would contain a unique line fixed by this complex subgroup GONO. And this Hicks algebra would act on this line because its functions inside this algebra is equivalent for against the GONO on both sides. So this Hx will act on a line, and we know that given an algebra acting on a line is the same thing as given a character of this algebra. So therefore, we would obtain a character that depends on this automorphic representation. So in fact, if your automorphic representation is everywhere unramified, then it can be recovered from all the lines that are denoted by L pi x. You just tender them up, you get and you use GONO to act on it, you will get you use GONA to act on it, you will get the automorphic representation. So in other words, so essentially the automorphic representation is determined by all these characters when x varies, at least when this representation is unramified. And now let's look into the structure of this spherical Hicks algebra. It's Hx. So we are working with GON, so the structure of Hx is very simple. So you can consider certain orbits, double cosets inside GONF. So here it's given by this element. So it's a diagonal matrix. This Tx is the uniform matter of Ox, and there are I of them and n minus I of 1 on this diagonal matrix. You use GONO to act on both sides. You get a coset. You consider the characteristic function on this coset. In other words, so this Hix is an element inside this spherical Hicks algebra Hx. So it is known that Hx is generated freely by H1 to Hn minus 1 and Hn and its inverse. So here, this Hn is invertible because, as you can see, when I equals to n, this diagonal matrix is contained in the center. So therefore, it's invertible. Okay, so it is maybe an exercise to verify this isomorphism, and we can write it in a very more canonical way as this Sn invariance inside this algebra. It's the polynomial algebra inside Z1 and Zn and their inverse. So this Sn, this symmetric group, acts in the natural way. So in other words, so on the previous page, we said automorphic representations, unramified automorphic representations are given by some characters of Hx, and now we want to get some character of this ring. And this character can be, and this character is determined by the value on D1 and Dn up to the action of Sn. In other words, they are determined by these values, this phi of Zi. So they are called Hicks eigenvalue of your automorphic representation at the local place X. So far we have introduced the two sets of eigenvalues. On the Galois side, it's Frobenius eigenvalues. On the automorphic side, it's Hicks eigenvalues. So let me also mention that there's an even more canonical way to write the above equivalence. In other words, so you notice that this ring is the ring of characters for representations of GON. So, or it's the Grothendieck K0 of rep GON of this abelian category after compactification. So this perspective will be useful when you want to study for general Retafu G. So let's go back to this page. So I just introduced these two sets of eigenvalues, and let's remember that this Langlands conjecture, or this Fox theorem, says that this bijection would match these eigenvalues. So you might wonder, so one of them is contained in C, the other, if you know it's contained in Q or bar, how to match them? So the answer is they are all algebraic numbers, and it makes sense to talk that they are equal. But these are technical things, let's ignore them now. Okay, now I want to talk about general diagonal groups. So Langlands conjecture can be stated, and as was in fact stated for general diagonal groups. So for simplicity, so I will assume our G is split over FQ. So in other words, it will contain a Cartan subgroup defined over FQ. So I know nothing about the general case. So in this case, we can also consider Galois representations and automorphic representations. You just replace G of n by G. So let's first look at the automorphic side. Just like before, so we should consider this spherical Higgs algebra complexable function on this double quotient. But in this case, so it is no longer isomorphic to Gaussian K0 of rep G. Instead, it's isomorphic to rep G K0 of rep G check. Here, this G check is Langlands dual group. So one quick way to convince yourself about this is you look at this double quotient. You will realize they are labeled by co-characters of G. More precisely, dominant co-characters of G. So in other words, they are dominant characters of G check, which is exactly the isomorphic class of irreducible representations of rep G check. So therefore, you will see this Langlands duality happening. So in other words, for Langlands conjecture for general diagonal G, you have to consider G on one side and G check on the other side. And if you make this modification, you can state the conjecture. You consider automorphic representations about G of A, and you consider Galois representations or homomorphisms of Galois group inside G check. You want some bijection or more weakly, some correspondence between these two sets, such that the Frobenius eigenvalues and Higgs eigenvalues would match. So you want to find such a thing, and here match means the following. So on the automorphic side, we can still obtain some characters just like before. So there are characters of this algebra, and they should match certain characters. They should match certain characters of this ring, and these characters are exactly the character of this corresponding to this conjugacy class. So I will just write like this. So from now on, I will just say that it satisfies certain Higgs eigen property, and no longer mentioning the exact meaning of this. So now let's come to our main topic. So I just give you a very quick review of Langlands conjecture, global Langlands conjecture, and now I want to talk about its geometric translation. So recall our X is a complete curve, complete smooth geometric connected curve over this finite field, and our F is the function field of this X. So we can actually translate both sides in Langlands correspondence into geometric objects about X. Let's first look at the Galois side. So an unramified Galois representation, sigma, is the same as a local system on your curve X. And for general group G check, you just put G check before the word local system. It's G check local system. So one way to define it is using Tanaka formalism. So it means for any representation of G check, you would get a local system of the same rank with this representation, and they should satisfy some condition. So more precisely, you should have a monoidal functor from rep G check to the category of local systems on X. So this is the meaning of G check local system. And knowing a sigma is equivalent to knowing such a local system. Now let's look at the automorphic side. So on the automorphic side, so previously, so if we focus on all automorphic representation, we should study functions on this quotient. But because we are considering every unramified representations, we are actually considering functions on this double quotient. And this double quotient, it has some geometric meaning. So with uniformization theorem, so its element can be identified with G torsors on X, automorphic classes of G torsors on X. And G-torsors are X, so they can be classified by a moduli problem. And because we want to consider them, we will not use the coarse moduli problem, and we will not use the semi-stable one. Instead, we have to use the moduli stack of all G-torsors. So this is because some G-torsors, such as the trivial G-torsors, it has many automorphisms. And if you want to make the entire family into a well-behaved algebraic geometry object, you have to use the language algebraic stacks. So for us, this bond G is an algebraic stack, and this double quotient can be identified with k-value point of this of stack. But this bond G, essentially, it contains more information than this double quotient because it's a geometric object. It tells you how these points are, in some sense, glued together. So as we have just seen, so both the Galois set and automorphic set, they have geometric translations. So therefore, we have this natural question. So we want to ask, is it possible to do this Langlands correspondence? In other words, construct the Higgs eigenfunctions completely in geometric method. So we can ask this question, and this was indeed the question asked by Lemon in 1980s, in early 1980s, and he proposed a way to do this, which is to use Grothendieck's function shift correspondence. Let me first remind you what's this. So let V be a nice enough variety over this finite field K, and let F be a sheaf, or more precisely, a complex of L-adic sheaves on this V. So in this case, Grothendieck gave the following construction. So you can consider a k-valued point on this V and choose a geometrical point x bar over it. And you consider the stock of your sheaf at this x bar, so which is a vector space or complex of vector space. So this F over x bar. So this stock is acted by the symmetry of x bar over x. In other words, it's acted by the Galois group of x bar over x. And inside this Galois group, there's the geometric Frobenius element. You consider the trace of this geometric Frobenius element, which is again some a number. So it's the sum of all the eigenvalues. And you can verify that this trace does not depend on the choice of x bar, because in some sense, all the Galois groups that are conjugate to each other. So therefore, we really do obtain a function only a number only depend on this small x, and therefore we obtain a function denoted by f of f. So this construction tells you that starting from a complex of L-adic sheaves, you can obtain a function on the k-value point of your variety. And this construction is particularly well behaved when you restrict it to perverse sheaves. I will not mention any more words about perverse sheaves, but you will see later that we will naturally turn to perverse sheaves. Also, I want to mention that this construction is compatible with some natural operators on both sides. So for sheaves, you can consider pullbacks and direct image, pullback and push forward. So in this case, we consider star pullback, which corresponds to restriction of functions. You can also consider Schwick push forward. In other words, integration, in other words, direct image with convex supported support. So this Schwick direct image, it corresponds to integration of functions. So maybe you know the sixth functor formalism of sheaves. You will realize that there are two other pullback and push forward that cannot be seen after taking this trace of Frobenius, namely this Schwick pullback and the star direct image. They are forgotten after you take this trace of Frobenius. And this actually reflects the, in some sense, the power of the geometric tools. So in geometry, in shift theory, have more functors. You have all these six functors and the adjunction before them. And there are some powerful methods to study them, like taking nearby cycles, like other things. So some of them cannot be seen on the level of functions, essentially because functions, in some sense, are discrete things, but these shifts, they can see actually how the points are glued together inside this geometric stack. And indeed, as we'll see later, so the construction called nearby cycles will play a role inside inside this proof. And nearby cycles, in some sense, it's a mix of star pullback and star push forward, or Schrick pullback and Schrick push forward. So which means it cannot be easily seen on the level of functions. Yes, but I'm not mentioning it because on Bang-G, so at least for the entire category, there's no such thing called valid duality because it's not quasi-compact. So, but for general B, what you said is correct. So there are more stories about this duality thing about Bang-G, so we can, if I have time, I will mention it. Okay, so this Grothendieck function shift correspondence gives you a way to produce functions on k points of Bang-G or on k points of this double quotient. So here I actually need to replace this double quotient by the geometric incarnation of them, so the loop group and R group. But this becomes the standard notation, so I will keep this notation. So then we will get a categorification of the spherical Higgs algebra, namely the spherical Higgs category, which is the category of perverse shifts on this double quotient. So the model structure is still given by convolution. It's given by some pull-push. So this model category categorifies Hx, and we can also consider this category perverse shifts on Bang-G X. It categorifies functions, the vector space of functions on k points of Bang-G X. In other words, the space of automatic functions. And as before, just as Hx acts on space of automatic functions, so this spherical Higgs category also acts on this category. So we will call this the Higgs modification action. It still depends on a place X. Okay, now recall that previously when we discussed the Langlands conjecture, we introduced the geometric we introduced the isomorphism to state the requirement that the Frobenius and Higgs eigenvalues should match. Now we also need to categorize it. So this is known as geometric static equivalence due to many people. So the following form is due to Kovac and Vinonen. So it says there's a canonical monodal equivalence between the spherical Higgs category and the category of representations of G-check, third-dimensional representation of G-check. So here the model structure on the left-hand side is given by convolution, and on the right-hand side is given by usual tensor product. So for therefore, for any representation of G-check, for representation V, we would obtain a perverse shift on this double quotient. We are denoted by this SVX. So it is actually some intersection combination shift on the Schubert variety of alpha Grassmann. So we denote it by SVX. And now we can state what's the geometric problem we want to find, or we want to tackle. So previously, we want to find Higgs eigenvalues. So it's some function, automatic function, such that it's an eigenfunction for all the for the Higgs spherical Higgs algebra. Now we want to find some sheaf called Higgs eigensheaf, which are some eigenobject for the action of this spherical Higgs category. So more precisely, we want the following. So on the left-hand side, you use this sheaf called static sheaf, SVX, to act on your F, which is a sheaf, which is a perverse sheaf on this Bang-G X. So you would obtain another perverse sheaf on Bang-G X, or a priori another complex of perverse sheaf on Bang-G X. So on the other hand, you require it to be just F tensor with some vector space, and this vector space is determined by your local system. Namely, it's just the fiber of your local system at the point X. But of course, you want to state this isomorphism in family of this small x. You want it to be actually a smooth family, a least family. So, and if you want to state the eigenproperty precisely, you also need to talk about associativity law and commutativity law, which I will not mention now. So in any way, so you can imagine you can categorize the notion of Higgs eigenfunction and obtain the notion of Higgs eigensheaf in such a way that if you take trace of Frobenius of this Higgs eigensheaf, you will actually obtain a Higgs eigenfunction. So therefore, our problem now becomes the following. So given a local system E, we want to find a Higgs eigenshift F whose eigenvalue is E. And once we have done that, we can take trace of forbiddance and get actually Higgs eigenfunction, and therefore obtain the Galois to automorphic construction in classical Langlands. So this was proposed by Norman in early 1980s for general G, and for G equals to GON, so this was solved by Frankel, Getgray, and Vinonen, so around the year of 2000. So they proved for any irreducible rank n local system E, so you can find, and actually there's a unique Caspidal Higgs eigenshift F with this eigenvalue, unique up to tensor ring with some vector space. So this proof was after Norfolk's theorem, and in fact, in the first proof, they used Norfolk's theorem. So the first proof was not a pure geometric one, but later, so Getgray around 2002, I think, so gave a pure geometric proof which does not depend on Norfolk's result. So in other words, so you can say that from that proof, so this at least for this question, you have a independent result inside geometric Langlands. So let me also mention that, so this conjecture for general G remains open, so even now, and it's still one of the main big problems in this field. And to be honest, I think people do not know whether or not this is correct. So maybe for some local system, you cannot find the Higgs eigenshift, we don't know. And there are some rumors that, okay, I will not say these rumors if Sam didn't say that, okay. Okay, now let's turn to categorical equivalence. So previously, our question is to find some eigen functions. I want to compare it with the following picture. So suppose we have a vector space acted by some commuting operators. So in order to understand this vector space, you can try to find eigenvectors. We can try to find that are simultaneous eigenvectors for all the operators, and then get a spectral decomposition of this vector space. Write this vector space as direct sum of something. So now, so in our case, we categorified vector space into categories, and we categorified eigenvectors into eigenshifts, and we can ask similar questions. Can we try to use this eigenshifts to give a decomposition of the entire category, the category of all shifts on this bound G? And this is a natural question that people would ask once they realize we can use geometry, we can use shifts to study this Langlands. So actually, this question has a very long history, dated back to 80s. So people want to study the entire category of shifts on bound X, in our case, complex of L-dic shifts on bound X. So as I mentioned before, this category contains more information than the space of unramified automorphic functions. And in fact, studies on this category have produced many new ingredients and insights into the Langlands theory. However, so you cannot naively expect some Galois counterpart of this category on the Galois side because of the following fact. So Galois representations, or in our case, local systems, they do not form an algebraic stack, at least when your base field is finite. So if you have not seen this, so you are encouraged to try to define such a thing, and you will encounter some problem. For example, like the characteristic of the base field, so they are not the same. One is over FQ, the other is over QL bar, and there are some more serious issues. So in any sense, there's no well-behaved modulus stack of local system on G-check in this L-adic world. Suppose there was such a thing. Suppose you can define such a fan moduli problem. So this algebraic stack looks as G-check. Then you can imagine, so you would conjecture that this category shifts on bound G is actually equivalent to quasi-coherent shifts on this modulus stack. So this is like the categorization of the spectral decomposition I mentioned before in the following sense. For each local system, in other words, for each k point inside this stack, you can consider the not k point, q bar point on this stack. You can consider the corresponding quasi-coherent sheaf called skyscraper sheaf supported at this point. And that skyscraper should correspond to the Hagen sheaf that we try to find. And in general, because any sheaf on this local system can be viewed as some integration of all the delta sheaves. So you can view a general sheaf on boundary X as some integration of all the Hagen sheaves. In other words, you obtain, in some sense, a categorified spectral decomposition. So, but you can only expect it if you can actually define this modular problem. Otherwise, you cannot obtain a geometric object. You just get some discrete points. And of course, you cannot expect Q-co on some discrete points to go to this category. Otherwise, this category would be semi-simple, which is stupid. Okay, so this non-existence of this modular stack of local system in the L-adic case over finite field was the main reason that people didn't state a categorical conjecture for more than 30 years. Didn't. So we do have a conjecture now, which I will mention later. But during these years, people first consider other sheaf theory rather than L-adic sheaf theory. So by sheaf theory, I mean it's some thing behaved like category of L-adic sheaves. For example, so you can consider category 0 case and consider the category of D modules. You still have these poor push functors, and you have like radial duality and something like that. Or you can consider the case when the base field is C, and you consider just sheaves on complex topology or constructor sheaves on complex topology. So this is called the Betti setting. So there are many other sheaf series that I will not mention. So these two settings that are related to each other by Riemann-Hilbert once you restrict to regular holonomic D modules and in the constructor sheaves. So in other words, they are close cousin of each other, but each of them would contain more information, and they do not directly talk with L-adic sheaves unless you use some other method, some motivic method, which I will not mention. So people considered like this geometrical Langlands problem in other sheaf theory setting, and I'm going to introduce these conjectures. So let's first look at the RAM setting. In other words, the case of D modules. So in this case, we do have a modular stack of the RAM local system, because the RAM local system is just a bundle with connections. So you can write down the equations to define a cover of this modular stack and prove its algebraic stack. So I denote this algebraic stack by this local system RAM. So we do have this, and now the previous heuristic idea tells us that D mod on bound G should be compared with quasi-coherent sheaf on this modular stack. This was the conjecture or the best hope proposed by Lin Chen in the 80s. So at that time, I think they already knew that this could not be true because of some phenomena of Einstein series. And like over 10 years ago, so Arinkin and Gatescray, they gave a precise formulation of this conjecture. So they enlarged the right-hand side a little bit. So in the following sense, so what the category on the spectral side, which I denote by indical loop, is certain enlargement of this Q-co. It reflects the fact that this modular stack of local system is not smooth. So it has some smooth locus if G check is semi-simple. So the smooth locus is exactly the locus when the local system is irreducible. But at the reducible local system, this thing is highly singular. And for singular varieties or singular stacks, there's difference between complex with coherent cohomologies and perfect complex. And this difference is inflected in this notation. So this right-hand side is actually larger than Q-co, which is the intercompletion of category of perfect complex. So on the automorphic side, this reflects the fact that the Hecke-Engen objects are not unique, then your local system is not irreducible. So I do not have time to explain this, but it also reflects the fact that in classical Langlands conjecture, when talk about reducible Galois representations, you need to be more careful to describe this correspondence using our packets. So this is the modification inside this conjecture. In some sense, this modification is technical, and for beginners, so you are welcome to ignore it. So it's less it's less important than some other loop we'll see later. So, but in fact, this modification, in some sense, it's very important in the proof, as Sam told you last week. Okay, so let's look at this conjecture. So I want to emphasize some feature of this isomorphism. So on both sides, there are some notion of bundles with finite connection. So on the left side, you are talking about D-modules. So we know D-modules, they are like generalization of bundles with finite connections. So they are, in some sense, sheaves with finite connections. So on the spectral side, they are considered the modern stack of bundles with finite connections. So one of them appear inside this category, D-mod, the other appear inside this space. So there are some, but not very perfect symmetry between the statement. And actually, so this phenomenon can be, I think, can be best explained by so-called quantum geometric Langlands conjecture, where you can deform both sides and this statement becomes symmetric. Or there's a thing called double geometric Langlands conjecture, where instead you consider T star on bound G and T star on bound G check the cotangent bundle, and the statement becomes symmetric. But this is something particular to the de Rham setting. So I think people do not fully understand what's the actual meaning behind this symmetry, at least mathematically. Okay, so now let me turn to Betty setting. So this de Rham setting was proposed by Benson Drinsford like 30 years ago. This Betty setting was much younger. So it was about 2015 by Benzi and Nadler. So in the Betty setting, you can also define the modular stack of Betty local systems, which are just representations of the fundamental group, or more precisely, fundamental group point. So this is a modular stack, recognized as a mapping stack. And you can state this conjecture, but it takes like 20 years for people to actually find the precise formulation of this conjecture, even after people realize you should use indical loop on the right-hand side. The reason is because on the shift side, on the automatic side, you also need to put some loop condition here. It's called shift loop, which is actually more important than the right-hand side. So I will explain this. So first, the definition of this is the following. So it's a full subcategory of shifts with nilpotent synchronous support. So for a general shift theory, you can define the notion of synchronous support, just like for D-modules, you can define the notion of synchronous support. And for Betty shifts, this is defined using macrolocal stocks. So, or if you want, using some nearby cycle functors. You can also define for your edge shifts. So as I said, this nearby cycle is something particularly for shift theory, not for functions. So therefore, it's not an easy, not an obvious thing to find what's the function theory analog of this category, of this subcategory. And in some sense, this is really some invention in this geometric theory, which did play a big role in the proof of the conjecture. So you can consider this shift loop. So this, I just give you the definition, but its actual role inside this Langlands theory was best explained by the work of Nadler Yun around 2015. So they explained that, so Hicke modifications on these shifts with synchronous support, so in some sense, very smoothly for these points x. In some sense, this Hicke modification, they are least over this curve x. But if you work over the larger category, work over the entire category shift x, so this Hicke modification, in some sense, they can have some jump with respect to points on x. In fact, I think they conjectured this property characterized this subcategory, and that was later proved by by these 6 authors. Okay, now we turn to the last setting, so which is the setting that can be applied by L-adic sheaves. So as I said, we do not have a modern stack of local systems in L-adic setting. However, so you can consider the formal modular problem. It behaves much better than the entire modular problem. In other words, you will only allow formal deformation of local systems. But more precisely, you should fix their semi-simplification. So use this idea, you can define a certain thing. So these authors define certain thing called local system with restricted variations. This local check restricted. It works in any shift theory setting. So if you want, you can imagine it is a formal scheme or formal stack, so which is the formal completion of all points inside the actually modular problem local check. But it's not precisely that thing, but you can imagine it to be that. So in other words, on the spectral side, we focus on the formal geometry. So then you have to shrink the category on the automotive side. You cannot just use the entire category of sheaves or even category with nilpotent singular support. Instead, I put a C here. So this means you consider the full subcategory of interconstructible sheaves with nilpotent singular support. So these people conjecture this equivalence, and they do have some evidence for that. So in other words, in the drama setting, you are consider regular holonomic D modules rather than all D modules with nilpotent singular support. So this is some category. So you might already be lost by all these categories, but let me mention that this statement is this conjecture is the conjecture that directly talks with classical Langlands conjecture. Namely, you can consider a certain operation called taking trace of forbiddance on the level of categories. And this and this automatic side, it will produce the vector space of automatic functions with complex support. So you will actually get the thing you want in classical Langlands theory. So however, if you work with other categories, so you will not get this. You really have to work in this restricted world to do this. And therefore, these 6 authors, the AGKRV, they proposed a precise formulation of spectral decomposition in Langlands conjecture like this. So this space can be realized as certain global sections on this arithmetic local system, which is the forbidden fixed point of that. So if you want the QL bar points of this arithmetic local system stack, is exactly the Langlands parameters, but so there are some fat points or formal points. So therefore, this global section, so it's just not the direct sum of K, it's direct sum of some finite dimensional vector space, which tells you something about the L packages. And here they are not using structure shift O, they are using do nothing shift, which is some technical point I do not want to talk. But I want to emphasize that in this setting, they do have some consequence in classical Langlands conjecture. And therefore, if you can prove this conjecture, so you will get this isomorphism, and therefore you can say you solve function field Langlands for general G. But unfortunately, we do not have a proof of that conjecture right now. Okay, now I want to mention the development in the title, so which is the joint work of Gatsgray and Ruskin, and joint work with Arinkin, Barado, Campbell, Fagerman, Kevin Lin, Rosenblum, and me. So this it will be contained. The proof will be contained in a series of 5 papers, and 4 of them are already on website now. So it says that the conjecture in the Ram setting and Beatty setting, so they are true. So we proved it for general reductive G. But we say nothing about restricted setting in LS case. So therefore, we cannot say that, we can say nothing new about original Langlands conjecture, except in general case. So I stated this theorem by saying the Ram setting and Beatty setting are both true, but in fact, so what we really proved is the Ram setting. So the Beatty setting is deduced from it using Riemann-Hilbert correspondence. Therefore, it's not the ideal proof or the proof proposed by Ladner and De Benzi, so in the papers. So they proposed to solve Betti Langlands using some topological method, like cutting the Riemann surface into some small pieces with some marked points. So that's a really beautiful picture, and might be the way to, I think in some sense, the correct way to prove this Betti conjecture. So instead, this is like a chip. So you pass to the other side of the Riemann-Hilbert and use some method in D modules to solve this. So, okay, so now let me restrict to this drum setting to the category of D modules on bound G, and I want to talk a little bit about the proof because I still have time. So in drum setting, the key question to ask is like how to control this category of D modules on bound G. So you can ask the question, you can ask Dennis this question or Sam this question. They might give you different answers. So for me, I want to say that we control it by using two local categories, denoted by KL and VIT, stands for Kaplan-Luke category and Vitaker category. So the definition will depend on small disks on this curve X. Therefore, we call them local categories. And moreover, we control them not just by these categories, but by the certain structure of these categories. Namely, so for disks on this curve, you can imagine two disks that approach each other and fuse into a single disk. So this category would have some prescribed behavior with respect to this fusion construction. And we use these structures to control this D-mod bound G. In more mathematical words, it means the following. So there's a thing called run space, which is like some exotic thing. It's just a presheaf. It's not a stack. It's just a presheaf on the category of all Athens schemes. It classifies finite subsets of K points on X. And if you replace K by S, it classifies a finite subset of S points on X. This is called run space, although it's not a sheaf, it's just a presheaf. So you can talk about like D modules on run space. You can talk about Li sheaves on run space. You can even talk about sheaf of categories on this run space. And the local categories I mentioned before, this Kaplan-Luke category and Vitaker categories, they are actually sheaf of categories over run space, equipped with some additional structure, which are called factorization structures. Roughly speaking, it means the following. So if you consider a finite subset of points of X denoted by X1 to Xn, so this is a point of run, you can consider the stock of your sheaf of category at this point, you will get a category. So this category should have a decompensation. It should be the tensor product of some other categories, only depend on each single point. In other words, you should have this. So here, the C stands either for KLG or with G. So in other words, so you can imagine if this is your X square, this is your diagonal X. If you put a point away from the diagonal like XY, so your category would be like C tensor C. And if you approach this diagonal, it would become C. And in some sense, so it's a deformation from the category C tensor C to C. And if you take nearby cycles for this deformation, you will get a multiplication structure on the C, at least when this nearby cycle is repeatable. And because there are many directions to approach it, so you actually get many multiplications for this C. So in topological world, this actually makes sense. And the factorization structure is the analog of what are called E2 structures. So factorization categories is closely related to E2 categories. So if you do not work with categories, you talk about factorization algebras or factorization sheaves. So there are also analog of other familiar objects in representation theory, like vertex algebras, chiral algebras, and other things I don't want to mention. But the language of factorization categories is actually the best thing to work with in the world of algebraic geometry. Although it's not like the cleanest language to do so. So in this series of papers, there are many words, like hundreds of pages, devoted to build the basic theory of factorization theory. So essentially, because we have to work with infinite categories and to be careful about some phantom objects with no cohomologies. So therefore, this is really the acne part of the proof. So it's some very important technique we used, which requires some work. Yeah, anyway, so idea is to use these factoring categories, these local categories, to control this D-mod of Bang-G. And now I'm going to tell you how to control this. So let's first look at the category. So as I said, it's a factoring category. So it's at a final set of point, it's the tensor product of some KLX. I'll tell you what's this KLGX. So it's a of representation theory definition. So it's the category of representations of Cosmodee algebra at critical level that are integrable for this art group GO. So this category was studied in the work of Kajan and Lustig, and they related this category with quantum algebras away from critical level. So we call it KL because it's related to the work. So as you see, this is really something from Lie theory. It's like representations of some F&D algebra. And if you know Bernstein's localization theory, which relate representations of the algebra G to the category of D-modules of like variety, you will realize that this is just an alpha analog of that category. So, and there's indeed an alpha analog of this localization functor, which goes from the category KLG, but actually over run space, to the entire category on Bang-G. So in finite the algebra theory, in localization theory, so you know localization functor, if you modify it, it's an equivalence. But in this affine theory, it's not an equivalence. Instead, it's almost a Vidal quotient. Like this category contains more information than that. In some sense, your quotient are ideal. But by the word almost, I mean, so this thing is kind of larger than the image of that. So more precisely, this Bang-G-X is not quasi-compact. If you restrict to certain large enough quasi-compact open of this Bang-G-X, so this functor would become Vidal quotient. So therefore, in some sense, you can control this category from the source by this KL. And the reason that this is helpful is because we can translate this category KL to the dual side, to the Langlands dual side. So by using the notion of G-check operas, this can be dated back to the work of Fagan-Frankel, so which I do not want to mention here. So in this series of papers, we put a lot of efforts to generalize Fagan-Frankel's thing to the factorization setting to overrun, and which says that this category, this KLG run, can be translated to the spectral side. So note that this is really something about the algebra, about localization theory. It only works for D-modules. So it is because of this tool, or mainly because of this tool, that we can also say anything about the LID setting. So because we use this to control this category. Now let me tell you the other control, so which is a geometric control, V-Tucker category. So it's the categorification of V-Tucker functions in classical Langlands theory. So namely, sorry, that's a typo. Namely, you consider the Affine-Grassmann, which is G of X quotient by G of OX. You consider shifts on this Affine-Grassmann that is equivalent for n of f against the Carter. So this n is the nilpotent radical of your Borel subgroup B, and this Carter is a non-degenerate one. So this category is known as a V-Tucker category, and it's equivalent to rep G-check. So if you have attended Breuermann's talk, you will realize this is related to something called FLE. So now this V-Tucker category can control this D-mod Bang-G from the target. So there's a functor called taking V-Tucker coefficients, go from D-mod of Bang-G to this V of G-run. So it's the classification of usual V-Tucker coefficients operation in classical Langlands theory. So we have this functor. So I will not tell you what's the definition of this functor, so you can treat it as a black box. But I want to mention that this functor is defined in pure geometry way, some push. Okay, now when we restricted the category that we are interested in, namely D-module with nilpotent synchronous support and Caspel D-modules, so Fragman and Ruskin, so they are among these 9 authors, so they proved that this functor is essentially fully faithful. or it's essentially conservative. So it does not lose any information. So this proof uses macrolocal stocks, in other words, some nearby cycles. They calculate this. They calculate this stocks. They related the stocks with some beta coefficients and be able to prove that that function is conservative. Suppose you can prove this function is fully faithful, then I think you can get rid of the Castanuzic category. You can just use this beta category in the entire story to control this demode from G and be able to produce a new proof of this conjecture. Unfortunately, so we do not know a direct way, a geometric way to prove this fully faithful, unless in the case of GON. So therefore, so we have to use this the other control, this control, this KO control. So it's because we do not have enough control for this function. And in some sense, this entire proof is to play with these two functors. So we use them to control this category and to translate to the automatic side, or to the spectral side, and try to finally deduce an equivalence using some formal nonsense. So anyways, this is the main idea of the proof. And what I really want to mention is that the proof has two inputs. One is from Lie theory, the other is from geometry. The Lie theory part, it's very beautiful, but it restricts our ability to work in other shift settings. This geometric part, so it's more complicated, and still something that are mysterious, but it has more potentials to unveil more things about this geometry Langlands theory. So anyway, so we do have this proof, and if it's correct, so we can call it a theorem, and we can say the geometry Langlands conjecture are solved in the unramified case in the Dirac setting. But this is not the conclusion of this field. So although it's it was the thing that people tried to solve for many years. So instead, so this is like a cornerstone on a non-unknown journey, because there are still many things that people care in this field, and much more important things. So for example, as I mentioned, you might want to find a pure geometric proof that works in the L-adic setting so that you can solve classical Langlands. So, or you might want to study the case where the group is not split. People do interested in this case, but I know nothing about this. Or you can study the ramified case, which is more complicated, and there are more interesting phenomena about it. And you can also study the ramified case in local geometry Langlands theory, which I didn't tell you what was them. So there are more mysterious phenomena in local geometry Langlands, and they're also very important. Also, you can consider like Langlands functoriality. So we have an equivalence tells us that two categories are equivalent. On the spectral side, you can consider a map from G1 check to G2 check, obtain a functor. You can ask what's the corresponding functor on the automatic side. And the answer is we do not know in general what's happening. And this is the categorification of Langlands duality. For instance, you can consider tensor product structure on the Galois side. And people wanted to know what can be translated to automatic side, and we don't have an answer. So it is definitely not the stupid tensor product structure on D modules. So it should be something more mysterious construction that might have to do with wonderful complication of G, but we do not have a precise formulation about it. And there are many other things in this geometric Langlands field that are still open, and I do not want to mention now. Okay, that's all I want. Sorry, that's all I want to say for today, and thank you for your attention.
Is there any question?
That's not a slide. That's not a slide. So you take
I
the
mentioned the what?
periodic shape case. It doesn't form a slide, and then you take the formal deformation, and then construct it from algebraic stack. But I just want to know what do you mean by formal deformation? Do you mean you consider it as a Galois representation and then deform that Galois?
Not really. It's in fact heuristic words. So by formal model problem, I actually mean the following. So we can define this restricted local stack, this model stack of restricted local system in any shift theory setting. In the Betty setting, so it's exactly like the formal completion of the entire stack. But you can also define it as classifying certain monoidal functors. And that definition makes sense in the LX setting. So more precisely, so the definition looks like the following. So recall, so I might make a mistake here, but let me try. So recall, so a local system is a monoidal functor from rep G check to these shifts on X. So now you want to put some S here. So you can consider certain monoidal functor from this rep G check to this category. S is testing scheme over QL bar. This is tensor over vector of QL bar. This is really a categorical definition. So it's a crazy idea to do this. So because when defining this, you might wonder like how many information you can get from this functor. So, but in some sense, you can view this as a general Tanaka formalism, but you really need to be careful about what's this. So here, in fact, I need to do in the combination, and I need to consider in the list, and I want to not just consider classical S, I have to consider derived scheme S. Moreover, I cannot consider all monoidal functors. I should consider like right exact monoidal functors. So that's the precise definition. So you really need to be careful to find the actual definition, but it's like this. And it's subtle because this in the list is not equal to the category of all local system Rx. In the list means it can be written as the union of finite rank local systems. Here it's the like all local system, like infinite Y. And if you use this, you will get something different. So in the S, any testing point over QL bar derived. But in fact, you work with attaining one. Essentially gives you okay. So you actually, in some sense, you should consider all S. But if your group is like, if you fix the semi-simplification, so then you can consider like attaining one. So as I said, there's no. Not very simple. So it's like yes, but it's not a semi-simple category. You derive category. Yes, derive the infinite category. So these two, the difference of these two things happens at negative infinity. So there are some. Oh, yeah. So the reason is like this. So if you look at what's happening at a near irreducible local system, so like if you really choose some E which is irreducible, and which gives you a point inside this, so this is actually a formal stack at this point E. So in other words, it's a formal scheme quotient the autonomic group. But if E is not irreducible, so then it has some formal different direction and it has some like non-formal direction. Has to do with the fact with Jordan blocks. Yeah, but I think this was best explained in the introduction of this series of paper HKRV, and you are welcome to take a look at this. So they explain this story better than me.
Clarify the relation between the coefficient functor and taking macro-local stocks?
So there are two different things. So the idea is there's something called basic beta coefficients. So which is in some sense, if it's like the following: you consider Vitager functor inside this VG run, inside this RepG check run, and you consider the component for trivial representations inside this RepG check. So which is a functor from D mod of func G to vect. So you obtain such a functor, and I will tell you what's this functor in terms of micro-local stock. Other Vitager coefficients, there are some conjectural description. So at least when your weight of your representation is dominant enough, but for general weight, it's still a conjecture. So for the basic Vitager thing, it's the following. So your D module is a sheaf on G with nilpotent synchronous support. So this nilp is a Lagrange inside T star G. So inside this T star G, there's a thing called global constant size. So which is like you consider Hitchin fibration. So it's the global analog of usual constant size. It intersects with this loop at a smooth point. More precisely, you should consider the loop a certain connect component of this loop. So it intersects with a certain connect component of this loop at a certain closed point, and that closed point corresponds to a cotangent vector of this func G. So therefore, you can consider nearby cycles along this. You can micro-local stock along this direction, which give you a vector space. And now the claim is that this vector space is equal to the basic Vitager coefficients. So you might expect other Vitager coefficients can be explained similarly by considering the intersection of constant size with other components, but it's still a conjecture.
Maybe I have a question. So you mentioned about Nadler, and Nadler is also famous for his work about Fourier category and mirror symmetry. Wondering if there are some.
Can I have some people from the audience to help me to answer this? So you can consult his student Peng Hui about this. I'm not an expert to really give you a satisfactory answer to this question.
Thank you.
So I prefer to refer this question to Peng Hui.
In one of your slides, you state that there's a problem in the existence of the modular stack on the local system.
Yes.
Yeah. So afterwards, you define 3 kinds of modular stack on the local system. So what is the criterion or principle in defining this stacks?
So in general, you can always consider some modular problem. Given a testing point S, testing scheme S, you can consider the thing classified by this problem, which in some cases it's a set, in some cases it's a grouped, in some cases it's a infinite grouped. So you always give a functor. So from the category of affine schemes, unramified functor to something. So this is like a modular problem. But the question is whether this thing is represented by a scheme or a stack or some more bizarre object. So like there are some necessary and sufficient condition for representability problem, like a classical theorem by Arkin and something like that. And this is about whether or not it can be represented by stacks. You can also ask whether it's represented by in the schemes, like this guy is in the scheme. So, and what I really mean is that the functor, whatever the definition of the functor you put here, so you start from S, you can try to invent some notion of local system in families over S. I don't have a good one, but you can try to invent such a thing. You will realize this is not represented by algebraic stack. This is what I mean. Yeah. So the naive thing, of course, does not work. So for example, you want to consider this guy, but this makes no sense. This S is over QL bar, this X is over FP, so you you cannot say consider like shifts on this with equivalent with some local constancy. So this doesn't make sense. So what I really mean is you can try to invent something put here that can be called like the entire model problem, and you will be in trouble. And the actual definition for restricted Y is this, and it behaves like the formal modular problem, but not exactly that.
Can you explain the meaning of canonical in the equivalence?
In the what?
Huh?
Canonical in what?
But what do you mean by canonical?
Okay. So these are bad words. So in general, I believe, so in a paper, you can delete canonical, you can delete all the words canonical, and you will lose nothing from a paper. So for me, it means it satisfies some condition that I do not want to mention. So, okay, so let's pick a random one. This one, because I'm more familiar with it. So this thing means the holding. So there exists a unique equivalence like this, compatible with Hake actions, compatible with Eisenstein series, and compatible with theorem chi as more of them in the torus case. This is what I mean by canonical. Other canonical means similar things.